So what I want to do was a shootout of some thread pool stuff. This grew out of the C++ talk, and Mark had mentioned that they're using um, thread building blocks at side effects. So I put a shootout, or I created a shootout and I added thread building blocks into the shootout. So just to summarize what I found, just taking a base algorithm, and again, I compiled it with both G++ 9.2 and Clang. And the basic reference case of, this was a Mandelbrot curve, I'll show you in a second. Just doing the basic thing, they're about the same, no big deal in difference, with no threads, so it's just sequential. And if you use a threaded for loop, so you thread the for loops, it speeds up. Now this is a 16-core processor, so it's speeded up about, what, 3.5 times on a 16-core processor? Something's wrong. And what it is the Mandelbrot curve. If you just divide the work by 16 and give 1/16 of the work to each thread, some of the threads finish early and some of the threads get stuck doing all the work. So that's why it's about 3.5 times, and the other 8.5 CPU cores are doing nothing. They finish early and that's it. And if you just do the same thing with OMP parallel 4, does the same thing, it parallelizes your for loop. So the results are somewhat comparable to what you can get with your own do-it-yourself threaded for. So next thing is to crank things up and start using our C++ 17. So if you use for each parallel, and you do it with G++ and Clang, you'll see that you're starting to get a bit of a difference. But if you do it for parallel unsynchronized or unsequential, then it goes even faster. And this one here, which wasn't so fast, is now the winner. And if you just say parallel in sequence, whatever, for each. So what this does, it uses your SIMD, your Neon instruction set if it's an ARM processor, your SSE if it's an Intel AMD processor. And so just using your SIMD instruction sets, it actually slows down compared to, well, that's about the same. So there's no gain, there's no benefit of using the SSD. And once you start doing the thread building blocks, you can see it starts to rocket, and our basic thread do-it-yourself thread thread pool is comparable. It's not as fast as the thread building blocks, and you can see this is a grain size of 1. So for doing the graphics image, that's 1 scan line per thread. And then it goes back to a thread pool, picks up the next scan line. If the grain size is 2, then that's 2 scan lines per thread. So each thread does 2 scan lines, then goes back to a thread pool and is assigned another pair of threads. So you can extend it and grain size 4, 8, 16, 32, 64. You can see diminishing returns and it's slowing down. So again, at this point, when you divide it by give each thread 64 scan lines, some of those threads finish early, some of them don't. So the heavy hitters get stuck with doing all the works, and some finish early, and there's lots of available cores with that aren't doing any work, and the other 3 or 4 cores are doing all the work. So that's basically it for what I wanted to. And to run the puppy. So this was the Clang compiler. So grain size 1, grain size 2. I think it's broken. I don't know what I did, but it's broke. These are, this should be around 100 instead of 17 or 15. So I broke it. Anyway, I guess that's it.